Hi, I'm Anagha Divekar.
Hi, I'm Santosh Putta.
I'm Fabian Juncker.
I'm Kamila Czachowska.
And I'm Aaron Tishnik. I would like to invite you to the Chatflow workshop at CYTO 2024, where we will be talking about how AI can potentially revolutionize cytometry. Feel free to view our video below, generated by AI, discussing reagents, controls, and other interesting aspects of flow cytometry, and come prepared to have a great discussion with us at CYTO 2024. See you in Edinburgh.
In the fascinating realm of cytometry, reagents and controls are the unsung heroes, playing a pivotal role in ensuring accurate and reproducible results in various cytometric assays. However, a lingering question remains: are our current standards and controls sufficient? And can we do better? Traditional methods of reagent design and manufacturing have served us well, but they may lack the precision and flexibility needed to address the complexity of cytometric assays. Ensuring consistency across different batches of reagents and laboratories can sometimes feel like a high-stakes balancing act. And how about the controls in cytometry? There are a plethora of factors not directly controllable, such as intrinsic variability in biological samples, spontaneous cellular changes, and environmental factors affecting specimens prior to analysis. How can we control these? Can AI help here? Artificial intelligence, a cutting-edge tool that brings promise to these challenges. Machine learning algorithms, one of AI's many tricks, can analyze vast datasets to identify patterns and help recommend optimal reagents, formulations, or clone fluorophore combinations, along with recommended controls. This can potentially enhance the precision and reproducibility of the reagent design, reagent stability, which reagents should and should not be made, and aid in the manufacturing processes. AI also has the power to revolutionize assay design. By enabling the exploration of novel approaches and optimizing parameters for improved performance, AI can help refine assay conditions and identify relevant biomarkers. This iterative process can lead to the development of more sensitive, specific, and robust assays. There are 3 pivotal points in assay design to consider. Implementing a design control approach to define assay performance requirements based on the intended use, including patient care and research applications. Assay specificity, which is crucial in understanding the biology of the target population, optimizing panel design, and selecting appropriate antibody fluorophore combinations to warrant specificity. An example is ensuring that different clones and fluorophores used for the detection of the same antigen deliver comparable results. For instance, for the detection of PD-1 on immune cells, more than a dozen reagents exist, albeit with highly varying detection efficiency. AI could rank these reagents according to performance and help optimize and standardize panels accordingly. And lastly, minimum number of events by applying Poisson statistics to determine the necessary number of cells to label and acquire for achieving desired sensitivity levels. These seem to be addressable issues for the AI tools. Can AI solve standardization of reported data? One of the key challenges in cytometry is the variability of reported MFIs or scales across different platforms and applications. Can AI provide transformed and normalized data, integrating differences in instrumentation to report standardized values? AI, with its uncanny ability to identify common features of biological markers, can help in creating more universally applicable reagents. Can AI facilitate design of universal reagents and optimized panel design? These AI-based approaches to control design can streamline workflows, reduce costs, and improve comparability between experiments and laboratories. However, the road to AI implementation is not without its bumps. Integration into existing workflows may require infrastructure upgrades and specialized expertise. Additionally, regulatory proprietary considerations and validation requirements must be addressed to ensure the safety and efficacy of AI-driven reagents and assays. In conclusion, the potential of AI to revolutionize reagent design, manufacturing, and assay development in cytometry is immense. By harnessing the power of machine learning algorithms, we can optimize reagent formulations, enhance assay designs, and create more universal solutions. While challenges exist, the benefits of AI in cytometry are undeniable, paving the way for advancements in research, diagnostics, and therapeutic development. But this begs the question: what does the future hold for cytometry and the role of AI? Will AI-driven solutions become the norm, or will they remain a complementary tool? If you would like to discuss with us on this topic, leave your comment below and join our live discussion at Workshop Chatflow at CYTO 2024.